Okay, projectile motion. This is projectile motion in 2 dimensions. We've already talked about projectile motion in 1 dimension. And there's only one axis that we have to worry about. That's the vertical axis. But now we're going to add the x-axis, okay? So what we have basically, try to draw one, is that we have a parabola that is the trajectory of this projectile, okay, and that's moving in this kind of pathway, and it's dependent upon 2 things. First of all, it is dependent upon the initial velocity, what that equals, and also the angle that it is shot at or thrown at. So when we have when we know these 2 things, just the initial velocity and the angle of its trajectory angle, we can find its maximum height, or we just call that y max. We can find its maximum range, so this would be right here, and this would be x max. And also we can find the amount of time it's in the air, and that would be just t max. Okay. So let's go on and look at a vector. Okay, so we have a vector here. It has the initial velocity of 45 meters per second, and it has a 50-degree trajectory. Okay. Now, one thing I just want to say here, that if we look at any position, okay. Now we have, of course, the parabola that's like this. Okay. So let's look at the parabola right around here. So if we look at right about here, okay, and we put coordinates on it and our vector, we have 2 vectors. We have the y and we have the x, okay? And the x vector never changes in the horizontal, okay? It's the same. When it gets to the top of the curve, right here, okay, all we have is the x vector and 0 for the y vector. Okay, then as it starts coming back around again, okay, well then the y vector increases, and actually this should be in the opposite direction. And so on and so on. So the x part of the vector stays the same as it goes down, and then it's exactly the y vector is upward when it goes up. Okay. So now let's figure out what the maximum time is in the air, find the maximum height, the maximum range. Okay. So we need to break down this vector into components, okay? So we have initial velocity. We want to break this down to the x component. So this would be v cosine 50 degrees, and then we had v sub x, or v sub naught y, and this is going to be equal to v sub naught sine 50 degrees. So for the vertical axis, we have the only acceleration is on the vertical axis. On the horizontal axis, the x, there is no acceleration. Okay, and basically we can define, and we just put down it's going to be 9.8 meters per second squared, of course, for g. That is the only acceleration in the vertical axis. And for the x, it's just going to be x, is going to be equal to the velocity times time. Basically, that is just this equation right here, delta x over delta t. Okay. So let's make some equations now for finding, say, let's look at for the vertical, what's happening. Okay, so if you remember from early on, we had this equation. And I'm putting the g in right now, that's why it's negative. Okay, so we have this equation here, and this equation we can use to find the time because it has t in it. We can also use this equation to find the displacement. Let's first look at finding maximum time in the air. Okay, so we're going to take this equation and we're going to make some changes. First of all, what is v sub naught equal to? Okay, well, this v sub naught is really only the component of y. So it should be this, okay? And since it is a y, then it should have the sine 50 degrees, okay? Times t minus 1/2 gt squared equals delta y. Okay, so I want to solve for time. Move up here. So solve for t. Okay, so let's take a look at, first of all, we have a projectile that comes up, comes back down, okay? This would be the first position of y. This would be the second position of y. y2 minus y1 is equal to 0. So now let's look at our equation. V sub naught sine 50 degrees t minus 1/2 gt squared. So now we need to solve for t. Now we know that when we solve for t, because we have a 0 right there, we're going to get one of the answers is going to be 0. So we don't really have to use a quadratic equation. This becomes v sub naught sine 50 degrees, okay, t equals 1/2 t squared. I'm going to take both sides and divide by t. This is going to give me v sub naught sine 50 degrees and equals g t divided by 2. Okay, and so we're looking for the time, so this becomes 2 v sub naught sine 50 degrees, and this equals t, so, and this is all divided by g, and this equals t. So now we can find t. So let's do that. So t is going to be equal to 2 times the initial velocity of 45 meters per second, the sine of 50 degrees. Change this right here. The sine of 50 degrees divided by 9.8. Now notice there is no negative here because we cancel that negative when we move one of the terms to the other side of the equal signs. Okay. And so this comes out to 7.04 seconds. So that is the maximum time the projectile is in the air, including in both axes. What about maximum height? Or we call this sometimes just Y max. Okay, so to find Y max, this equation right here is a good one to use. And we can change it around to fit what we need it to use for. So first of all, as the projectile goes up to Y max here, it's Y1 and Y2. So we're actually trying to find Y2 minus Y1 equals, in this case, Y max. It also has, of course, its velocity, which is initial velocity. So we need to use the Y component of velocity. And so what is our Y component of velocity? Well, it is V sub x y is equal to V sub nod sine 50 degrees. Okay, so now we just need to plug this in this equation. Squared. And then this is equal to, we'll put the negative for the g, and then this y, was the delta y, we can just call this y max. This is what we're trying to solve for. And so y max is going to be equal to the minuses will cancel out, sine 50 degrees divided by 2, 9.8 meters per second squared. Okay. So let's plug in the values. 45 meters per second, sine of 50 degrees. This gets squared. Okay, and then we have 19.6, 2 times 9.8. And this comes out to 60.6 meters. So that is the maximum height that reaches the projectile, the ball, rocket will reach. Okay. Now, what about the range? Okay, so the range, or just X max, can be found by using a simple equation. This equation, delta X over delta T. Because when we look at the X-axis, what's happening, there is no acceleration as it moves until it falls back to the ground again. There's no acceleration in this axis. And all we have is constant velocity. Okay, we got to remember now to use the proper velocity. That's the X component. So what is that? The X component velocity is X is going to be equal to V sub nod cosine 50 degrees. Okay. So now we want to make sure though, now we have this equation right here, let's put it into a form of x. Delta of x is going to be equal to v delta t. Okay. So we just got to make sure that we substitute the v and the delta t with the right stuff. So this delta x right here, this is going to be the maximum x. I'm going to subscript it as maximum x. This velocity is going to be this right here. V synod cosine 50 degrees. And it's going to be times a time, and that time, it has to be for maximum range, it has to be T max. And we found T max earlier. So it's always good to find T max first in these types of equations. Okay. So this, let's plug everything in here. We have 45.0 meters per second. The cosine of 50 degrees. Okay, and then we have the time, which was 7.04 seconds, and that gives us 204 meters. Okay, so let's just kind of look at what we solved here. So we had a projectile take a route similar to this right here. Its range was equal to, or X max was equal to about 204 meters. Its maximum height, Y max, was 60.6 meters. Okay, and we also had a initial velocity, and angle was 50 degrees with V synod at 45 meters per second. And then we had the total time that it was in the air. You just put this sort of represent ground, was T max. 7.04 seconds. Okay, so that's how you find a simple two-dimensional projectile motion problem. This is part one. Part two is going to be a projectile off a building. Okay, so that's it.